Hi, everybody. Thank you for coming to this session. We're going to talk about optimizing Apache Hive performance in HDInsigh. So before we start, I'd like to do a quick survey. How many people here use Hadoop? So not a lot. My next question was, how many use Hadoop in production? Only a couple. And do you use HDInsigh, the two hands that went up? Do you use HDInsigh or on-prem, or what do you guys use? Sorry? How about you? OK, got it. Great. So all the things we're going to talk about usually apply to any Hadoop flavor. But I'm going to focus more on HDInsigh for obvious reasons. But if you use even Cloudera, you should be able to use it. OK, so let's talk about the session objectives and takeaways. In this session, we're going to learn more about HDInsigh and Hive. I'm going to spend 5 minutes on it. I assume you know it. If you don't, in 5 minutes, we'll do a quick crash course in that. The bulk of this presentation would be on discussing various optimization. And then we're also going to see what's coming up in HDInsigh. The key takeaways, my hope is by end of this presentation, you are able to be convinced that Hive can be optimized and can be very fast. You know the set of optimizations to choose. And so you have an inventory of optimizations which you can go tune. And finally, if you are not on Hadoop, which seems like the majority of people here, if you are using like a relational data warehouse today, you are convinced that Hadoop and Hive can actually replace that. So let's start by talking about what is HDInsigh. So today, if you want to do Hadoop on the cloud, you have two options. The one on the right is Hadoop running on infrastructure as a service. The one on the left is using HDInsigh. So if you are coming from on-prem, so someone who uses Cloudera or Hortonworks or MapR, the easiest way to start running on the cloud is just to rent a bunch of VMs and to deploy the bits, right? But that's still a lot of work on your part. If you have an on-prem cluster, you still manage it. So it's infrastructure as a service. What we have done is, the one on the left is platform as a service. That's HDInsigh, where we manage the bits. So all you do is you click a button. We deploy the Hortonworks distribution on our VMs. We've already tested it thoroughly. We monitor it. We deploy it. You can scale it. So HDInsigh makes it very easy, where you don't even have to worry about managing your cluster. We do that for you. You just worry about writing your own applications. So when you do click on HDInsigh, when you do pick HDInsigh, you have a bunch of options. You can optimize the cluster for you can optimize it for batch, MapReduce, for pig, Hive, HBase, Storm. So we have different options. You can pick one, the ones for the scenario you'd like. So that's what HDInsigh is. By the way, given how small the audience is, if you guys have questions, just raise your hand, and we can take that. But I have a lot of content, so I'd like to move fast. So if it's a lot of questions, I'll just skip, and we can do it in the end. So this is my last slide on HDInsigh. HDInsigh is a fully managed Hadoop and Spark for the cloud. It's based on 100% open source Hortonworks data platform. Once you click on create a cluster, within 15 to 20 minutes, you have a cluster up and running. It's supported by Microsoft's industry best SLA. Familiar BI tools for analysis. We have an ODBC driver. You can hook up Tableau, Power BI, whatever you'd like. We also have deep integration with Visual Studio, IntelliJ, and Eclipse, if those are the tools you'd like to use. Out of the box, we have connectivity with open source notebooks. And according to a study, the cloud is 63% cheaper than on-prem. So this is just the reason why you should be using HDInsigh and not any other vendor. OK, enough of my sales pitch. Now let's talk about technical stuff. So quick intro to Hive. So what is Hive? So Hive actually was incubated at Facebook back in 2005, 2006. The reason Hive came about was people were writing MapReduce jobs. And if you have ever written one, even to do a simple word count, it's hundreds of lines of code. So it's pretty complicated. So Facebook realized that, and they came up with Hive, which is essentially SQL. Underneath, it converts it to like MapReduce. So you can see since over the last 10 years, there's been a lot of innovation. So in 2006, after it was incubated at Facebook, in 2010, it was made an Apache project, which made it a lot more innovation started happening. In 2012, we had ODBC, JDBC drivers. In 2013, we introduced TES, vectorization, ORC. In 2015, ACID was introduced. So now you can actually do updates. And finally, in 2016, we're introducing in-memory. So in memory through LLAP. So that's like Spark. Like Spark has in memory, when Hive will start having in memory. And I actually have a demo at the end. If you guys wait long enough, I can show you the demo. I know there's a party at 5. So one quick pitch on what Hive enables data warehouse. If you saw my last slide, the goal here is we want to do everything that SQL can do. So if you have a traditional data warehouse, you want interactive, you want sub-second, you want ACID merge, and eventually you want to build a cube. So that's the goal. We're not there yet. But together with Hortonworks, we're working on making Hive, making it enterprise data warehouse ready. All right, so let's talk about now Hive on HDInsigh. So this is how you create a cluster. I usually give a demo of this, but I'm going to just breeze through it. Once you come to the Azure portal, you click on New, you click on Data and Analytics, and you click on HDInsigh. And then right here, you can choose your cluster name. You can pick what type of cluster you want. If you click on this dropdown, there are different options. Like I said, Hadoop, Spark, HBase. Traditionally, on-prem gives you everything in one box. We like to keep it separate because if most of our customers come to Hadoop for a particular scenario. So why waste your resources running different things if you're not going to use them? So you just pick your scenarios. So since this presentation is all about Hive, we're going to pick Hadoop. You can pick operating system, Linux or Windows. It's your choice. Customers prefer Linux, so Linux is our preferred flavor going forward. And then you can choose your tier, standard, or premium. With premium, you get a bunch of other things. Right now, it's R server, which allows, I think you saw a demo before, but R server allows you to run distributed R on Hadoop. But we'll be adding more and more things to the premium offering. So once you create a cluster, this is how it looks. You can go to your cluster dashboard. Clicking on that will take you to Ambari. Ambari is the portal to manage your cluster, deploy, run jobs. So it's the portal where you can monitor everything about your cluster. This is built by Hortonworks, and if you are coming from a Hortonworks on-prem, this is exactly the same thing you get. So you'll just feel right at home. Clicking on Hive, clicking on Configs, clicking on Add Advanced, you'll see a bunch of options. So the reason I'm showing you this is we're going to talk about a lot of optimizations. So you should know how to change those optimizations. This is where you can change it. And this, if you scroll down, almost every optimization we talk about can be changed here. That's one way to do it. The advantage of doing this is it's persistent across sessions. The easier way to do it is you can just type those settings in command line interface, but it only persists for that session. But if you're doing a quick dev, if you're just a developer trying to get things done quickly, you can just do it on command line. I'll show you how that looks. But if you want something in production, this is the way to do it. OK, so any questions so far? OK, so there are 2 scenarios that we'll talk about today. That Hive is basically used for 2 scenarios, ETL and ad hoc. And these are 2 separate design patterns which have separate set of problems. So what is ETL? ETL just means taking raw data from a bunch of sources and preparing cooked data, right? So our customers who use ETL are typically the personas are developers. The cluster, so they choose to have a dedicated cluster which is always running production jobs. They would rather it not be shared with anybody else because if you do, you have strict SLA on your jobs. And if you share your cluster, those jobs will be affected. The job pattern is fire and forget. So you just want to fire the job and not worry about it. And so you want to be able to program it. And the typical job is full table scan, large joins. It's a pretty big job. So the problems here that customers face is how do I run my jobs fast? What tools do I use? And what file formats should I use? So that's the ETL side of things. On the other side, we have the ad hoc and exploratory. And the persona here are data scientists. Their job patterns are typically, they're using a shared cluster, right? So they are typically running short-running jobs. And it's ad hoc jobs over cooked data. So there are a different set of challenges. How do I share my cluster? How do I optimize my final output so that when customers are querying, data scientists are querying, the response goes faster? So essentially here you want super fast responses, right? Like seconds. We're not talking minutes. We're talking seconds, hopefully sub-second. So in the rest of the presentation, we're going to look at this and talk about the optimizations and fill the last row, which is what are the optimizations we can do for each of these scenarios. So here is how the HDInsigh architecture looks. When you click on create a Hadoop cluster, the stuff in the dotted the dotted black box, everything inside comes with it. At a high level, there's ETL clients, and then there's BI clients, right? The ETL clients use SDK or PowerShell, and they talk to Templeton, which is our fire and forget interface. And the BI clients use JDBC, ODBC, Visual Studio, Hue, Ambari, and Beeline, most of the other tools, and talk to Hive Server 2. The difference is with Hive Server 2, the client always has to have a session open, whereas with Templeton, you don't have that. Underneath it, they're all doing the same thing. The execution engine is preferably Thais, which is faster than MapReduce. It creates AMs, application masters, which creates DAGs, which ultimately runs on Azure VMs. Two things to point out here is, one, we use our metastore is Azure SQL metastore. It can be persistent. So if you, by default, you get one, but you can have a custom metastore, which means it can be persistent. And then our storage is also persistent on the cloud, which can be Azure Blob or ADL Store. I'll talk about that in the end. The key point here is both metastore and cloud store are persistent. So you don't have to keep your cluster up and running 24/7. You can run it for 1 hour a day, delete the cluster, come back the next day, and as long as you point it to the metastore and the cloud storage, it's like your cluster never died. So you save so much cost while your cluster is not running. So that's the power of using Hadoop on the cloud. OK, so with that, let's talk about optimizations. So I have a laundry list of optimizations going down the Hive stack. We're going to first talk about job submission. So in the job submission phase, we will talk about how to make jobs submit faster. A typical Hive query takes seconds to minutes to start. How can you make it faster? The second one is execution engines. What are the Hive settings we can do to make your queries run faster? Then we're going to talk about the different storage formats or file formats, org, JSON, and compression. And finally, which file system to use. So the first one is job submission. So in the job submission, if you think about Hadoop when it was first introduced, or Hadoop 1 as we call, it was built for batch. At a very high level, a job is launched. A bunch of resources are acquired. Once it finishes, those resources are let go, and the job ends. That works great if your job is running for hours. The problem is, to just grab those resources, it takes 60 plus seconds, right? So your first minute is always spent just trying to launch this job. So Hadoop 2, sorry, I have my slides a little bit here mixed up here. Hadoop 2 actually fixed this problem. How did it fix this problem? It introduced this. So Yarn came along, which is a new operating system for Hadoop, and it introduced this concept of app master. What an app master can do is it can stick around for a long time, right? So app master can hold other containers, which is where your job runs, and this app master can stick around for a longer time. And so if you use app masters properly, you don't have to pay the cost of starting these, grabbing these resources, because they are properly pre-provisioned. And that's what Hive Server 2, which was introduced after Hadoop 2, that's what Hive Server 2 did. Hive Server 2 does two things. One, it gives you ODBC, JDBC connectivity. And number two, it's the bridge to connect your query to the application master. So put another way, every time a new query comes to the Hive Server 2, it will spawn a new application master and run your query there. All this, hopefully that made sense. The problem is, we don't know, when you create a Hadoop cluster, we don't know whether you want it optimized for ETL or for BI, right? If you want it for ETL, you don't care about the startup. If you want it for BI, you would like this. The problem with BI, though, is if the AMs are always in memory, they're using up resources. And so if you have 3 or 4 concurrent users, now you're eating up the space. So by default, it's turned off. But you can turn it on. So going back to the things I mentioned, how do you improve the query startup performance? There are 3 things you can do. Number 1, decrease the session startup time. So as soon as you start your query, it takes about 30 seconds to start this app master. So if you can somehow save the creation of that app master, you can save the 30 seconds. Like I said, if it's a BI query, it's very important to do this. But the downside is the more application masters you put in memory, the more resources you're eating. So there's a trade-off. You got to decide. But that's one thing you can do. Secondly, even if your application master is up, your query doesn't run in the app master, right? The query runs in the containers that the app master has. And these containers, if they're reused across queries, it'll run much faster. So if there's some way you can tell Hive Server 2 to keep those containers and make them available for reuse. That will make your queries faster. And the third setting is, is there any way to keep your containers around longer, even after the queries finishes? So those are the three things you can optimize. And here are the three configurations you can do. So the first one is, the first top three, I'm looking at these three right here, are how do you maintain persistent resources so that your session is fast, right? So when you create a new session, it comes up right away. The next one is the pre-warm resources. How do you actually pre-warm the containers so that as soon as the session is up, these containers are ready to go? And the last one is you can just disallow complete shutdown. So once your query is done, how do you tell Hive server to not? These are the containers it should always hold. So even after the query dies, these containers are still around. Now, one question could be, why don't you set this to 1,000, right? Let's set the last one to 1,000. The problem with that is the moment you set it to 1,000, basically you've used up all the resources for your cluster. And if this is your own cluster, great. Your queries will run super fast. But if anybody else tries to run a query, it'll fail because all the resources are for your query. So with these three settings, you can avoid the 15 to 30-second startup time that Hive has. And so here are some settings that we recommend. So the first three, which we talked about, are the persistent ones. You should just set it to true. The queue should be set to default. And the test sessions per default queue should be set to the max number of concurrent queries, which reflects basically how many users you expect to have in your system. The next one is pre-warm enabled. You should set it to true with the number of containers set to 5. And the last one is number of containers. You should just set it to like 1 to 5, because that's what it means is those are the containers which are always held and never given up. Now, it might be the case that when your query is running, there are more than 5 containers needed. So that's the time it will spawn up more. But at least the 5 containers that are hot and ready to run can be used right away. Any questions? I know I'm going fast, but any questions? OK. So we talked about the first layer, which is job submission. And we're going to go to the next one, which is execution engine. At the execution engine layer, we're looking at the Hive and Taze optimizations. So one thing just to understand a little bit more about why future concepts, so I think we should discuss Java process and Yarn containers. So what is a container? A container is a unit of work in Taze. So every time you want to run a Taze job, it actually runs in a container, right? So there's a container which runs a Java process, and within a Java process is basically your query elements. So like all the buffers or the data structures like sort, buffer, hash tables that you use. Now, the reason we're discussing this is a lot of times you need to understand that you have to stay within the container boundary. And so an naive approach is just to say the Java process should be equal to the Yarn container size. But that's not the case, because Java, if you tell it to stay within 1 gigabyte, for example, it can often exceed it because of its garbage collection. So the key thing to remember here is your Java process should be about 80% of your Yarn container size, so that there is some leeway if it expands. So why this is important is for the next few optimizations. So we're going to look at join, and this is one of the, if you're doing ETL, this is one of the key optimizations you can do to improve your improve performance. So joins are the most expensive in any query. The way joins work in Hadoop and Hive are mappers read the input, then there's a shuffle stage where these input keys are merged, these key value pairs are merged, and then that's the most expensive stage. So if we can do anything to avoid that, that would significantly improve performance. So there are 3 types of joins that Hive has: shuffle join, map join, and sort merge bucket join. And we'll discuss each of them. And then I actually have a demo to show you, just to show you how, if the same query I run with 2 different joins, what the performance difference is. So shuffle join is the default choice. If you start up your cluster and don't pick a join, this is most likely what will be picked. It's a default choice. It always works. And it works like the way I explained it, right? So you read from one of the tables, you bucket and sort on the join key, and then you use a reducer where the join is done. There is no Hive setting needed. It works most of the times. The next one is map join, which is the most optimal one. This works as long as you have one big table and one small table, and the small table can fit in with the big table where the join can happen. So if you think about it, each mapper has, so there are two mappers. Each mapper has the small table in memory, so it can just do the hash right there. So the reducer is not used for join here, only the mappers. And you can do that by using this Hive autoconvert joins true. It's very fast, but like I said, it's limited because how many times do you have a big table and a small table? But when you do, you should use it. The third one is also very efficient, which is the sort merge bucket. If you have two tables, both are sorted and bucketed on the same column, you can use this. And it's very efficient and very fast. Again, the downside is you have to do a lot of work to prepare the data. Right? So these are the three joins. And now let's focus on one of them. So I'm going to show you how the difference between map join and shuffle join. And so before I start, I'm just going to run my query while I explain the theory, because this takes a few minutes to run. Okay. So my query is running, and I'll come back and explain you. So we're going to look at the map join optimization. An example being select star from a big table and a small table, where x from big table equals to y from small table. Like I said, what ends up happening is the small table is streamed to each mapper, which is where the join is done. This is very performant, in some cases up to 10x as much as shuffle joins. The cons are, like I said, must fit in RAM, and if you estimate wrong, your queries will fail. So how do you tune this? You actually turn it on by setting Hive optimized bucket map join equals true. Sorry, Mike, it was supposed to duplicate, and I think I'd like to have the mouse pointer here. OK, I still don't see it. OK, right there. So you can turn it off using this. You can turn it on using this setting right here. More importantly, you need to tell Hive the size of the small table, right? And that is something you can adjust using this setting at the bottom, Hive autoconvert join no conditional task. What you're telling Hive is this is the size of the small table. And remember, going back to my container conversation, I just explained to you it has to stay within the Java process. So whatever you're setting this value to, it has to be less than what your Java process can take, right? So now let's see this in action. So I ran this query. I ran two queries here. The first one, I said set Hive autoconvert join no conditional task size equals 1. So what I told Hive is there's only one byte you can put in for the extra table, right? And so when I run it, it ran in about, this is the first time when I set it to 1 right here. You guys can see this, right? I cannot see the screen, but you can see the code, right? So you can see the output. I set the size to 1, and you can see there were 2 mappers and 2 reducers. This is the reducer where the job was actually done. And this query ran in about 30 seconds. Then I ran the same query, except I set it to 500 megs. So what I said is, hey, Hive should be able to cache up to 500 megs of my smaller table, right? Once I do that, let's make sure I entered it correctly. This is where I entered it. And I look, suddenly my plan has changed. Remember, I had 2 mappers and 2 reducers here. And now I have only 2 mappers and 1 reducer here. Why is there no 1 reducer? Because that reducer was doing the join, which has now gone to the map stage, right? So you can see with the map join, not only that, the query ran about 35% faster. It's 20 seconds. It was 30 seconds. This is very small data, by the way. This is just 10 gigs of TPCH query. The reason I just did 10 gigs is because I wanted to be a little bit interactive, because otherwise this query would take minutes. But you'll see a lot more drastic gains if you go to hundreds of gigs or even terabytes. But so that's an example of one setting which can optimize your queries. Okay. So I have a few more demos like this. Hopefully that made sense. Any questions? Okay, let's move on. Okay, so the next one is, I'll just not make it big screen because it's confusing PowerPoint right now. So the next one I'm going to talk about is controlling number of mappers. Let me just run the query, and then I'll come back to explaining it. Let's do the theory first. So again, if you want to make your queries go faster, you should be able to control the parallelism. Now, there are two ways to control parallelism: controlling the mappers and controlling the reducers. So let's talk about the mappers first. How do you control the parallelism of the mappers? So Hadoop is built around this concept of divide and conquer. So essentially, all your data is read in split sizes, which is then used by containers to run maps and do parallel processing. Now, this split sizes is something that Hive picks by default for you. That said, you can actually tune them. And you need to figure out what the splits, if you know what the split sizes are, you can actually reduce your latency. So and a lot of times customers say, hey, my query was running for 20 minutes. Can you help me bring it down to 10? If you just, there's no real formula. You have to try brute force your way. But if you play with the split sizes, it might improve. So how do you do that? You can change it by, if you're using the MapReduce engine, you can change it to mapred.max.splitSize. Or you can change in Tez, there are two settings, the Tez grouping min size and the Tez grouping max size. How this works is Tez just picks a default split size, and then you define the grouping min size and the grouping max size. And then what Tez Hive does is it looks at what it calculated, and if it's lower than the min, it will pick your min. If it's higher than your max, it will pick your max. So it'll either be the min or the max, depending on what the default it picked, and it'll choose one or the other. So depending on, if you adjust your these two settings, you can see how many mappers were created. So in this particular example, I'm going to show you an example. Again, I ran a query, and we're going to go see the results. What I did is I ran 3 queries. In the first one, I used 500 megs of my minimum size. In the second one, I ran in, I think, 52 megs, and in the third one, 5 megs. So I basically reduced it by 10 every time. What I expect to see is there's least parallelism here, because this is pretty high. There's more parallelism here, and there is quite a lot of parallelism here. Right? So let's see that. So my queries ran. So the first one was very high, and it created only 16 mappers and ran in about 40 seconds. The next one, I divided it by 10, so it's about 52 megs. It created, remember, not 16, it went up to 150 and ran in about 24 seconds. And if it's 5 megs, it created 210 and ran in 13 seconds. So again, you may or may not see this gain, but in this particular query, it helped. And there's a limit to how much this helps. If you keep going, at some point, it'll just pick whatever makes sense. So, but that's something to keep in mind, that you can control the parallelism for your mappers using this. Just like you can control your mappers, you can also control your reducers. So I'm going to run this query again. This is the example for reducers. So what are we doing in reducers? I'll explain this query in a second. But why should you even worry about controlling the parallelism in reducers? So I'm going to talk about this great feature called ORC in a few minutes. ORC is columnar store. So the idea is if you have ORC, it can take your 100 gigs file and make it like 2 gigs. So 25 to 50x compression, super fast, sounds awesome. So you learn about it, you go try it. The problem is when you run this query, your data, you just have a 1 gig file, right? And as you run your query, you see that you're stuck in your reducer phase for like minutes, because even though it's 1 gig, there's not a lot of parallelism. So why is that? Because by default, Hive has a setting for Hive exec reduce. Like this setting basically defines how many bytes each reducer can have, which may or may not be suitable for your workflow, especially for small queries. You may not be enough. So that's why if you tune this, you can increase the number of reducers you have. So again, let's go back to the example that I submitted. So I'm going to run the same query twice. The first time over here, it uses the default. I didn't specify anything. I just ran it out of the box. So at this point, Hive uses the default value of that setting, which is 256 megs, right? So it it just calculates the size of the final output divided by 256 and creates as many reducers. In the second case, I run the same query again, but I change this setting and say instead of 256 megs, which you use 10 megs, right? And I expect to see more reducers here. So let's see if that happened. So again, I ran this query twice. The first time with I didn't touch the setting, and it created 39 reducers. The second time, actually, let's see. Here's where I changed the setting to 10 megs, and I see the number of reducers were increased to 1,009. Now, whether or not, in this particular case, I think it a little bit helped with performance. So it went down from 30 seconds to 20 seconds. But again, the key point I want to just bring about is you can change the number of reducers just by tuning a few settings. So any questions so far? I know, go ahead.
Is there any relationship between the size of the coverlet and the number of cores?
So is there do number of cores define the mappers and reducers? So the more cores you have, the bigger your container size, usually, right? So if you have more cores, it will have different resources, and the query, the plan will be different every time. So you'll have to try it on different cores to see what happens. So to answer your question, there's no direct relationship, but it'll be different because the resources available are different. Any other questions? OK, so let's move on. The next one, I don't have a demo, but it's just something that you should use. It's very simple. You should just have it on. Hive 13 came with this new feature. Hive 13 is Hive 0.13. Came with this new feature called cost-based optimization. What this does is it just creates more statistics on each table. So usually, it's very hard for an optimizer to generate a good plan when it comes to, it knows the input data, but it doesn't know what the query is going to do and what the final output data is. So with cost-based optimization, it can figure that out a lot more because it can also see the characteristics of the data. So what's cost-based optimization? You can ask Hive to create some statistics, which can then be used by the query optimizer to better build a plan. So again, the easiest way to, you should just use this. It's just a good thing to do. And Hive takes care of it automatically. All you need to do is once you're done with your table is ready, you just have to type analyze table customer compute statistics. This will create the table statistics. And you can also create column statistics. We recommend doing both. And for best results, do both. And then Hive will take care of it. It'll just make all your queries run faster, especially if they're joins. So that's cost-based optimization. The two other optimizations, which one is vectorization and one is Grace hash join. So what is vectorization? Vectorization tells Hive to able to process 1,000 rows together. So this was actually joint work between Microsoft and Hortonworks. This only works with ARC file, and it can increase your performance 3x to 10x. By default, this is on, so you don't have to do anything there except use ARC. We are also bringing text file support is expected to come soon. So vectorization with text, so that will even speed up regular text files. In addition, the second optimization here is Grace hash join. What is Grace hash join? I talked about the 3 joins before. Sometimes some joins fail. If you say Grace hash join equals true, it'll just make sure to try. It basically tries again with different types of a join. So there's a performance penalty you're paying, but if you're just running a one-off ad hoc job and you're willing to pay the penalty, this is a good choice because there's a good chance it might work. OK. The next one is some Tez settings. So we briefly touched upon the Tez application master. Again, just to remind you, every time you run a query, Hive Server 2 creates a Tez application master. So one thing that customers often ask is, how do I tune the size of my Tez AM? And usually 4 GB is enough. Even for the most complex queries, this is not something you should be able to change. You should need to change, but if you do need to change, you can tune it with this setting right here. The 2 other things, though, that might bring a lot more impact to your queries is, firstly, Tez automatically times, like the Tez AM automatically times out after certain, after being idle for some time. So you can tune that, and that's great because now if you have an AM, again, you're saving the time of keeping the session up, right? So you can configure that using this setting right here, which is Tez session AM DAG submit timeout seconds. We do not recommend having it more than 1 hour. There's still some bugs that might be there. So up to 1 hour is what's supported. After that, it's unsupported. And then you can also define the min and the max release timeout. So what this means is if you, again, the Tez AM has a bunch of containers. You want to keep those containers running as long as you can so that every time a subsequent query comes, it can reuse them. At the same time, you don't want to block the resources. So using the min and the max setting, you can control how long they should stick around. I know I'm throwing a lot of things at you, so I built a table. You can essentially go back and refer to it. If you just go back to the Ignite website, I'm sure the presentation will be there. But essentially, I have the HDI defaults here and the recommended settings here. And we've talked about a lot of these. So yeah, I think the only one I want to talk about is the last one, which one thing I didn't mention in the Tez container min and max is in some queries, it so happens if it's a long-running query that you have many mappers and you have a bunch of reducers, except the reducers are waiting for the mappers to finish. So even though Hive might have allocated the resources for the reducers, they time out, right? Because the mappers are still going. So in that particular case, again, changing these two settings will make sure your reducers are still around by the time your mappers finish. So again, you're saving time. So any questions on the whole execution engine optimizations? So the question is, what does Tez AM stand for? AM stands for Application Master. Every time you submit a job using Hive Server 2, it creates a Tez Application Master. Yeah.
So would you set all these settings at the cluster startup, like a bash script or something like that, or how would you?
Good question. So the question is, where do you set these up? Like I showed you before, there are different places to set it up. I just set it up right in the, if you saw, I just set these up right here in the command line interface. This works, but the moment I hit exit and get out of this session, these settings are gone. It'll go back to the default. So again, this is great just for trying things out. But once you are sure you want to do it, you will go back to the Ambari and the initial screens I showed you where to change them. That's where you would do it. OK, moving on.
Would those activations carry on the cluster, though, with those settings be?
So that's also a good question. Would they stick around? They would not. So if you restart like I mentioned, if you delete your cluster and create a new one, they would not stick around. So the way to do that is you can actually define them if you have an ARM template, which is what customers use to like if you're creating and deleting clusters every day or something, you don't do it manually. You have a template to do it. Right in the ARM template, you can define all these settings. OK, so we will talk about the different storage formats and the file system. Those are the two that's left before I show you the LLAP demo, which I'm excited about because it'll make Hive in memory. So then we'll stop talking minutes and hours, and we'll just talk about seconds. OK, so partitioning. If you're coming from the database, if you've used databases, it's the same concept. Partitioning allows Hive so that it doesn't have to read the entire table for every query, right? Especially for filtering. If you can just hit the right partitions, that's all you need, right? So that's what partitioning is. The way it works in Hive is when you ask it to create partitions, it creates subfolders where each folder lies, there's a partition. So just a couple of caveats. Like I mentioned, if you create 1,000 partitions, there will be 1,000 folders. And Hadoop in general is not good with too many files. So I recommend not having more than 1,000 partitions. Number one, so that was number one. Number two, always do not under-partition either. So try to use partition, like partitioning on sex doesn't make sense because you'll just have two partitions. Partitioning also on the other extreme, partitioning on state is also not a good idea, because Vermont, I don't know the population of Vermont, but some states have 1 million and California has 30 million. So just keep that in mind. So use partitioning wisely. Okay, so the next one is compression. This is also another interesting one. So let me just, again, I have a demo here, so I'm going to just submit the query while we talk about the, sorry, I exited from the Hive command line. So this is an example of the 30-second, like it's waiting for the AM to come up. It finally did. So if you had set those settings, you wouldn't have to wait the 30 seconds. So I don't practice what I preach, but you should, because I do ETL. You guys probably do interactive. Okay, sorry, bad joke. So in compression, I'll come back to this in a minute. Let's first talk about the theory. So compression is pretty powerful because Hadoop jobs are usually I/O bottlenecked. And so if we can compress the data, there's less data that needs to be transferred over the network, right? And so people think doing compression is awesome. So there are different types of compressions right here: gzip, bzip2, LZO, snappy. The key thing I want you to look at is the last column, splittable. What that tells you is if you have a compressed file like gzip, it cannot be split by Hive, and you lose all the parallelism, right? So gzip is a very bad choice. Even though that's widely used. It's a very bad choice for bringing data into Hive and then trying to run jobs on it. You should try to use bzip2 or LZO if it's indexed, especially for text. So just to show you what I mean, I ran 2 queries. So this is what I did. I have 2 tables, line item and line item gzip. Both of them are pointing to the same data, right? If you look, it's right here. And if you want to actually look in the store, right, we can actually go here. This is my Cloud Explorer. So it's like a storage, it's like a file explorer for the cloud, for the Azure storage. And under compression, I have 2 directories, raw, which is a 7 gig file, and I compress the same thing to 2.2 gigs, right? And I told Hive that there are 2 tables pointing to each of them. And I run the same query, except one is running with raw and one is running with gzip. And if you look at the results, the one running with oh, it's not letting me go up. The one running with raw has 206 mappers. I don't know if you can see that. Sorry, it's not letting me scroll up or point at the same time if I let go of the thing. But right here in the center, it says 206 mappers. And the one with gzip only has 2 mappers. So obviously, this second query is going to be very slow because you've suddenly gone from 206 parallelism to like 2. So that's why gzip is not a good idea. So choose the right compression. Okay, I mentioned this briefly, columnar formats. So other than text, you can use columnar formats. And what is a columnar format? So instead of storing data on a per row basis, you can ask Hive to write data for a column contiguously stored on disk. And this is really good because if you think about it, all your queries are usually using a column, right? When you're doing a filtering or a grouping or whatever, you're usually doing it on a particular column. So if you store everything contiguously on a disk, it can be very fast. That's the pro. You have to pay a price for everything good in life. And the con here is you have to convert the data to this columnar format, which can take a while. So the key learning here is you should use columnar format wisely. If you expect a lot of people to, like for example, in a scenario where you have a bunch of data scientists or BI tool users who want to use a cooked data, you might want to convert it to ORC, to a columnar format, because it will make it very fast. So there are 2 types of columnar formats, ORC and Parquet. I recommend using ORC because it just works great with Hive. It allows vectorized execution. It allows ACID. I'm going to talk about in-memory in a few minutes. And in-memory only works with ORC. So ORC is the way to go if you're planning to stay within the Hadoop and the Hive world. If you're planning to now interoperate with Spark or other things, there the ORC support isn't great. So that's when you should use Parquet. But in general, every time you have data that will be living around and you'll have a lot of, you'll repeatedly write queries on that data, columnar format is a good choice. OK. I'm going to skip a couple of things just because we're running out of time. For JSON, this is another common question. How do I use JSON with Hive? The answer is Hive has limited support out of box for JSON. There are 3 ways to do it. These are the 3 UDFs. The first 2, UDF stands for user-defined function. The first 2 are what's supported out of box. This is OpenX Surday is a third-party Surday. So the first 2, which comes out of the box, are not very they're not very easy to use, right? If you ever try to use them, it's not very efficient. Almost every customer I've talked to who uses JSON uses this last one, OpenX Surday. And if you want to learn more about how to use it, just search for JSON and Hive, and you'll see a document actually from Microsoft about this. So again, just to keep in mind, if you are going to start using Hadoop, you will sooner or later use JSON. And if you go back to this slide, you can just learn about OpenX. So that's what you should be using. OK, so we're done with storage formats. I have 10 minutes left, and I want to also leave some time for questions in the end. So the last set of optimizations we're going to talk about are file systems. And this is especially for people who are coming from Cloudera or on-prem. HDInsigh is a little different. And let's talk about why that is. So one of the most powerful things about running Hadoop on cloud is you can separate storage and compute. So what does that mean? If you have an on-prem cluster, you're using the same nodes for both compute and storage, right? So as you put more and more data into your cluster, remember, at some point you might need more. You run out of space. So what do you have to do? You have to increase the size of the cluster, right? So essentially, both if you run out of compute or storage, you have to keep increasing your cluster on-prem. On the cloud, we separate it out, right? HDInsigh has a persistent storage, which is a separate service and much cheap, which is called Azure Storage, which you can use for your storage, and compute runs on our VMs. So that's one of the key differences. Now, that's the good part. The downside, which someone might say, is, hey, aren't there limits on this cloud storage? Like, is it as optimal as your local disk? And the answer is, we actually found, some of our customers found that that is true. In some cases, there is a bottleneck. And so what a lot of our customers did, and just to put things in perspective, like I'll just give an example. If we have an Azure Blob Storage account, what they did is they learned about this partitioning, which I explained, and said, let me partition my data. They partitioned it, and this is one directory, this is one directory, this is one directory. They had 3 directories with the different months of data in them. And now when they started running queries, Azure Blob Storage puts a bottleneck. And so your queries start running slow. So we looked at that and said, hey, what you should do is you should create multiple storage accounts. So firstly, if you're a customer, you would not be happy about it. You say, that's more work. Why should I do it? You take care of that. But for a minute, let's say you like that. You're like our partner, and you're willing to do it. So they tried that. And what ended up happening is they created 3 storage accounts. And they put a particular partition in one storage. Second partition in storage account 2, third partition in storage account 3. Even this wasn't fast enough. Can someone tell me why this wasn't fast enough? So the reason it's not fast enough is because even if it has to read the same partition, all of them have to go to the same storage account. So the key thing here is what worked was actually putting the different parts of the same partition across the different storage accounts. So in the last one, partition 0, part 1, part 0, 1, 2, and 3 were all in Azure Blob Storage 1. Here, we sharded it across the different storage accounts. This worked, but it's a lot of work because you also have to change your query. So no one wants to do that. So that's why we created Azure Data Lake Store. That's a separate session. If you should guys at Ignite, those of you at going at Ignite, you should look at it. If not, just search online, and you'll see a lot of. But Azure Data Lake Store is cloud, improved cloud store, which has no limits on file size, massive throughput, and you can use this to improve your cloud limits. OK, so bringing it all together, I'm done with the list of optimizations. Now, here is the cheat sheet which you can go take away. Depending on your scenario, you can actually decide what optimization to use. So if you're using ETL, you should choose partitioning. You should turn on cost-based optimization. So this is where you put the statistics on the table. You should increase the tails container size if needed for large joins, because that will also increase the Java's heap size. You should try to use map join or sort merge join. You should tweak the reducers when necessary. You should use org file. You should use Azure Data Lake Store. And you should use bzip2 for compression. So these are good for long-running jobs. Pretty much all the same things can also be done for interactive, like the ad hoc and exploratory. But the 4 that will make the biggest difference is use ORC, right? Because again, it'll make every query faster. Choose different cluster than batch jobs. You should really have 2 clusters. And one of the things that HDInsigh brings is you can create 2 separate clusters, both pointing to the same storage and the same meta store. And it seems like it's the same cluster, but now you have 2 dedicated resources. They're not contending with each other. Yeah, so you should improve your session startup time and pre-warm containers. So with that, I want to just show you the future, where we're heading towards. We're very excited about this. This is Hive LLAP. It's actually being released in a couple of weeks. So what is LLAP? That requires a presentation of its own. In like 3 sentences, LLAP is a new hybrid model which combines both daemons and containers in the same cluster. What this does is, in the daemons, it can store data and can be cached. So your first query that it runs, when you run your first query, it just runs it using Tez the regular way in the container model, but it stores all the data it touched in these daemons. If you run the same query again or same type of query again, it'll first check if it's in your cache. If it is, it doesn't go back to the disk. It just reads directly from the cache and responses. So your first query might be slow, but subsequent queries are very fast. And how do you know whether it touched the cache or not? This is just an output from Beeline, which is a client to see, which is a client to run Hive queries. And you can see in this case, it hit the cache for whatever, I don't even know, 611 megs, I think, or 6 gigs. So 6 gigs it had cached, and it was able to find it, so it didn't have to go to disk. So I'm going to show you a quick demo of LLAP. Before I do that, I want to show you the cluster configuration. Since this is LLAP is still not out yet, it's not in a production cluster, it's in a dev environment. But here are the 2 clusters I have. This is my dev this is my dev cluster, which is LLAP. It says interactive Hive. And I don't know what happened here. This is my production batch cluster. So this is a batch cluster. This is an interactive cluster. All I want to show you is the number of nodes. You can see worker nodes are D14, worker nodes are D14. Right? They both are using the same. They both are created with the same settings. So you don't think this is fake. And I'm going to open a new window. So this. So what I'm doing is I'm going to run the same query on both the clusters and see if the performance increased. So I go back. This time, instead of using Hive command line, I'll use Beeline. Let me try to put them side by side. Maybe that'll take too long. Okay. So again, just to summarize, the the one with the green font is my batch cluster. The one with the orange font is my LLAP cluster. I'm going to run a standard TPCH query. Why do I keep saying TPCH? TPCH is an industry benchmark for databases. So I'm going to run a standard query on TPCH standard query and see on both the clusters and see what happens and what the performance is like. So the green one should take longer because it's batch. The orange one should take less amount of time because it's interactive. So while this is coming up, any questions I can help answer in the presentation?
Is that associated with an open source project or a certain component?
This is correct. LLAP is being worked on by Hortonworks, so it's completely open source. It's not something we've built. So you can see already the green one finished in about 17 seconds, while the orange one, I'm sorry, that's the interactive one, already finished in 17 seconds. while the green one is still going on. If you go up, you can see the number of cached bytes was 600, 6 gigs. So this finished in 43 seconds. This finished in 15 seconds, like 17 seconds. So you can see there's a lot of potential for gain. And this is just a dev cluster. We're coming out in public preview in the next couple of weeks. So you should try it, and you'll be, we're now getting to the level of all the excitement about other products. So I have 2 minutes left. I'm going to just end with this slide. This is where we are today. If you remember, I started with this. We have ETL clients and BI clients all talking to the Hadoop cluster with Templeton and Hive Server 2. But as you saw, different optimizations apply to different type, like depending on whether ETL or BI, different optimizations need to be applied. One size does not fit all. So this is our vision. What we're going to do is we're going to release a new cluster type called Interactive Hive, which I just showed you a demo for. So we envision you will have 2 clusters. One is the regular Hadoop cluster, and one is the Interactive Hive new cluster, exactly like I showed you, except one will be suited for ETL and one will be suited for BI. Both of them are using the same metastore and the same cloud storage. Both of them are persistent. So with this, it'll be like it's one cluster, but you really have two clusters underneath. This can be running 24/7 because you want to keep memory in cache. This can just run for 1 hour a day, so you can save costs. So this is our vision of actually building an enterprise data warehouse where you now can do both interactive and ETL with the same compute. So that's all I had. I guess the key takeaways again, Hive is fast. I know I threw a lot of optimizations at you. You can use this deck later. And you should really think about moving your enterprise data warehouse to HDInsigh and Hadoop on the cloud. So that's all I had. Questions? Actually, before you go, could you please fill a review for me? That would be good. Review the session so I know what I can improve next time. Thank you.
Yeah, regarding the ODBC thing,
That's right.
used for the SSIS maybe?
Yes. So ODBC, anything that can accept an ODBC can use that. So ODBC goes through Hive Server 2. That's what I threw in the BI client. What's your question? I didn't understand. Like,
Right. I just wanted to know that ODBC, that way, even a non-Microsoft.
That's right. Tableau works with ODBC. ClickView works with our ODBC driver. Yeah. We don't build our ODBC driver. We've outsourced it to Simba. Simba builds the ODBC driver for every big data technology out there. So world leaders are building our ODBC drivers. So all those settings can be configured. The main reason we created a new cluster type, which is called Interactive Hive, is for the same things, is because we want the entire cluster to be able to cache it. So if you use a plain vanilla Hortonworks build, like on-prem, you will have to choose what percentage of cluster you want for batch or interactive. But in our newer cluster, 90% of the resources will be saved for interactive. So to answer your question, we save almost everything. So your question is the map join. If there are 2 joins, like I said, as long as one fits in memory, it should work. Yeah. That's what I did. I picked one which was 6 gigs, one which was 300 megs. Okay. I think it should work. Yeah, I think it should work. I haven't tried. It may or may not work. I will have to try. So.
The second question is, if ETL browser has multiple steps, RC file for your
Depends. Creating an ORC takes time. So if you are willing to, like you have an SLA you're trying to meet, ORC will help downstream. Like if you have a lot of steps, sure, ORC will help each of those steps down the road, but you're paying a penalty to convert to ORC. So without like understanding more and trying it out, I cannot give you an answer, because the key thing is how long it takes to convert to ORC. That can change your answer. You don't have to worry about it. That was just an example of what people did in the past. You can just use Azure Data Lake Store, and we take care of that for you. But if to answer your question, you can just create multiple storage accounts, and there's a way to configure in HDInsigh cluster to use all of them. And when you use your query, you put the storage account name, so it knows where to go. Go ahead.
At the end of the presentation,
Yeah. So not everything will work. I will just say of all the big data technologies, this is the most mature out there to make that goal. Yeah, yeah. So I'm sure there'll be problems. I'm not. I mean, that's the reality, but we're getting there. And settings to make even reading data faster. So it's a bunch of both. So even if my point is, even if it doesn't go through cache, even my first cold query is much faster than a traditional test query. And we can talk offline. I can send you like all the optimizations that are done, but at a high level. Yeah, sure. Like I said, LLAP should be a 1-hour presentation on its own. Maybe next time. 3.5, so 2.5, HTTP 2.5, which is coming out in a couple of weeks.